Alright, ladies and gentlemen, chapter 3.2 here. Light passes along an optical fiber. What happens to the light within the fiber itself? Now, whenever you see the word optical fiber, straight away you should understand that it is basically the application of total internal reflection. So looking at this answer here, obviously D is going to be the answer in this case. Question number 2, light travels in a vacuum and then enters a glass block. The speed of light in the glass block is 2 times 10 to the power of 8 meters per second. Which statement about the speed of light is correct? The speed of light in a vacuum is 1.5 times, possible, because speed of light is 3 times 10 to the power of 8 meters per second, right? The speed in the glass is the same in the vacuum, not possible. Speed is slower in glass. Speed in the glass is 1 time, no, not possible. Speed in the glass is 1 times 10 to the power of 8 times the speed of her. This is not possible as well. So logical answer is definitely A here, guys. Alright. A ray of light in glass is incident on the boundary with air. State what happens to the ray when the angle of incidence of ray is less than the critical angle here. Now today, if the light is going less than the critical angle, what's going to happen is it is actually going to refract, right? In fact, it will bend away from the normal. The light will refract and bend away from the normal. Then after that, the next question here, the grade is greater than the critical angle. If any incident angle is greater than the critical angle, then obviously total internal reflection occurs. Okay, then moving on. Figure 6.1 shows a ray of light incident on a glass block at A. The critical angle of the glass is 41 degrees. Okay, so the critical angle here is 41 degrees. Looking at this one here, this incident angle is more than the critical angle already, right? So I know for a fact that total internal reflection is going to occur here. On figure 6.1, without calculation, continue the ray from point B until it leaves the glass block here. So without any further calculation, you'll probably want to use a ruler here as well, or you're going to draw a light ray that is going to go through total internal reflection, meaning to say this is going to be 60 degrees. Then once you have that, you're supposed to draw your normal here. And since it is going from glass into air, right, from more dense into less dense, it's supposed to bend away from the normal. Yeah? It's supposed to bend away from the normal, meaning to say this angle here must be greater than this angle here, which is essentially a mirror image of this thing here, right? And after that, the next part here, they ask you to calculate the refractive index. Since they already give you that the critical angle is 41 here, from here you should use the formula n equals to 1 over sine c, which is 1 over sine 41. Press that into your calculator. 1 divided by sine 41 here. You're supposed to get a refractive index of 1.52. The refractive index will be 1.52. There's no units for refractive index, so I'm trying to be funny and write something there. Alright, then moving on to the next question here. The speed of light is 3 times 10 to the power of 8. This is going to be your C. The speed of light in a transparent liquid is going to be 2 times 10 to the power of 8. This is going to be V. A ray of light is incident on the surface at an angle of incidence of 40 degrees. This is your incident angle. Calculate the refractive index of the liquid. In this case here, I have to use the C over V formula, which is going to be 3 divided by 2, which will give me exactly 1.5 here. You're supposed to get 1.5 here. Then after that, using the refractive index, they ask me to calculate the angle of refraction. The formula is n equals to sine I over sine R, right, which will be 1.5 is equals to sine 40 divided by sine R here, right? So if you press that into your calculator, you'll get sine 40 divided by 1.5, then shift sign the answer as well. You're supposed to get sine R is equals to sine 40 divided by 1.5. R will be shift sine 40 over 1.5. You press that into the calculator and you're supposed to get an angle of 25.4. 25.4 degrees, guys. Alright, and looking at this next question here, which usually a lot of students they've mistaken. Figure 7.1 shows a side view of an object at the bottom of the tank. The light travels slower in the liquid. On figure 7.1, draw two rays from the object into the air. Use these rays to locate the image here. Now in your IGCSE exam, a lot of students, when they do this question, what they'll do is they'll draw something like this and something like this. Then they realize that, oh, the light ray is too deep ray, so they go 90 degrees downwards like this. This is absolutely going to be wrong. Instead of doing that, what I recommend doing is you start from the object here. You draw two light rays that are going to bend a little bit away. Right, then after that, you're supposed to draw your light ray diagrams. That is going to look something like this lah. Right, it's going to look something like this. It should diverge here, guys, because if it diverges here, your virtual light is going to converge somewhere here, right? Right, then making sure that this line is a straight line and this line is a straight line. Wherever the dotted lines will be, guys, wherever the dotted lines will be, wherever the dotted lines meet, that is where your image will be, guys. Always start from the object to the eye instead of the eye to the object. Alright, then red light traveling in the air strikes the curved surface on a semicircular glass block at P. Figure 8.1 shows the ray of light. The light travels in a straight line from O to Q. It travels in a straight line here. You'll notice that it did not refract simply because it is 90 degrees to the surface. And from here, that's the next question they want. Explain why the light does not change direction as it enters the glass block at P here. It's because the incident angle is 90 degrees. This is because the incident angle is 90 degrees. The light will not bend in this scenario here. Or you could even mention that the light ray is moving on the normal and will not bend, or anything along the lines, right? Okay. Then moving on to the next part here, the light travels in the glass to Q, where it strikes the edge of the block at 30 degrees to the normal. It's 30 degrees to the normal here. The light ray then emerges into the air. It emerges into the air from glass to air. Obviously, it's going to bend away lah. The refractive index is 1.5. Calculate the angle between the normal and the ray of light that emerges in the block. They're basically asking you to find this angle here lah. Now, in your IGCSE exams, they love to give you this. A lot of students, they make the mistake is that they understand that, okay, right now the refractive index is n, and this is 30 degrees, right? Since this is the incident ray, they'll think that this is the incident angle I here. So what they'll do is they'll do n equals to sine I over sine r, right? And then they're going to put this into here and they'll put this into here. If you do that, right, you'll realize that your whatever r that you find is actually going to be much less than 30 degrees. So I think if you do that, you'll get somewhere around 17 degrees or below lah. But that's not the point. If you get 17 degrees and below, then something is wrong, right? That this here is supposed to bend away from the normal. If anything, this should be greater than 30 degrees, right? So you have to, like I was saying, you're supposed to understand that whenever you're using the n equals to sine I over sine r formula, your I will always be the angle that is in the air, and your r will always be the angle that is in the glass or medium or water or whatever, okay? So using that information, you're still going to use n equals to sine I over sine r. You're going to substitute the 1.5, and you're going to substitute this 30 degrees into your r. So in reality, you're looking for I, sine 30 here, right? So obviously in this formula, it's going to be sine I is equals to 1.5 times sine 30 here, right? And your I will be shift sine, bracket 1.5 times sine 30 here. If you press that all into your calculator, 1.5 times sine 30 and then shift sine this answer here, you're supposed to get an angle of 48 48.6 degrees, guys. You're supposed to get 48.6 degrees here. Alright. Then on figure 6.1, sketch the path of right ray after it emerges from Q. Obviously, this one here will be 48.6 degrees. It's supposed to bend away from the normal, guys. Alright. Then moving to the next question here. Oh, the last question here. The direction of light ray striking the curved surface of the block is changed. The angle between the ray and the normal gradually increases from 30 degrees to 90 degrees. Describe what happens to the light that strikes the block at Q as this angle increases. So this question here is basically saying that, oh, let me rub all this away. They're basically saying that this angle here is gradually increasing. It's going to increase to 40, 50, 60, 70, 80, and then finally 90 here. Now, if you think about this, this is essentially how the light rays, as you increase this angle here, guys, as you increase the angle here, initially it was bending like this. Once you increase it, obviously it's going to bend more. If you increase it again, it's going to bend more. Eventually, you're going to reach the critical angle here, where the light ray is going to go through maximum angle of refraction, right? This is basically your critical angle. Beyond the critical angle, obviously what's going to happen is total internal is going to reflect. Total internal reflection is going to occur all the way until it is 90 degrees, where it will yet again just shine directly straight through here, guys. So you're supposed to structure your sentence like this here, right? So if I were to structure this, it will be something like, as the angle of incidence increases, the angle of refraction will increase. It will increase all the way until critical angle is reached. This is when maximum refraction occurs. Beyond the critical angle, total internal reflection occurs and the light reflects in the glass block. Finally, at 90 degrees, the light is going straight through the block. Okay, so this is what you're supposed to say, guys. As the angle of incidence increases, the angle of refraction will increase. It will increase all the way until critical angle is reached. This is when maximum refraction occurs. Beyond the critical angle, total internal reflection occurs and the light reflects in the glass block. Finally, at 90 degrees, the light is going straight through the block. And this is how you're going to get your full 3 marks here. Alright? And moving on. An object is placed before a plane mirror as shown. The student views the image of the object in the mirror at P. Where does she see the image? So she's looking at here, the object is here. Now, logically speaking, if you want, you could draw the light ray diagrams. You could draw it here, and then from here, you're supposed to realize that, oh, it's going to be somewhere around Dong T, right? So, yeah, this one is just a little bit on the imagination side. Nothing much to explain there. The light has a speed of 1.24 times 10 to the power of 8 in diamonds. What is the refractive index of light? You are supposed to use the N equals to C over V formula, which is 3 times 10 to the power of 8 divided by 1.24 times 10 to the power of 8. Press that into your calculator, and I think you're going to get somewhere around 1 point something, right? 3 divided by 1.24. Oh, you're going to get 2.42. You're going to get 2.42 here. Which statement describes monochromatic light? Monochromatic light are basically single colored light with one wavelength and one frequency, right? So light does not refract, the light that has single frequency possible, light that spreads out and shines through a glass prism, light that travels at the same speed in all materials. No, it is definitely single frequency or single wavelength here. Now, this is one of the questions that I realize a lot of my students, they get it wrong as well. Scout P signals Scout Q. This is Scout P, guys, signals Scout Q on the other side of a valley using a mirror to reflect the sun's light. Which position allows the sun's light to be reflected onto Scout Q? Now, a lot of my students, they actually circle this as the answer. But if you think about it, right, if this is the answer, wouldn't the light bend downwards like this? Because angle of incidence should be angle of reflection, right? And if it bends downwards like this, who's going to see the light ray, right? So instead it should be A as the answer, guys, because if it is like this, the light ray is going to bounce like this, right? Which is essentially bouncing to Scout Q here, right? So A is definitely the answer here. It takes a little bit imagination of how the light rays are supposed to go as well. Okay. Now after that, a prism is made from transparent plastic. In this plastic, the light is traveling at 0.8 C, where C is the speed of light in air. Light enters one face of the glass prism at the right angle here. The light just escapes from the glass from the sloping face of the prism. What is the angle O here? Oh, now if today you're looking at this question here, there is a few components that you need to know, right? Since they give you the speed of light here, you can use the n equals to c over v formula, which in this case here, it will be speed of light in air, which is c, divided by the speed of light in the plastic, which is 0.8 c, right? Press that into your calculator, is basically 1 divided by 0.8. You'll get a refractive index of 1.25 here. Since you have the refractive index and you know that the light ray is going through critical angle here, guys, it is essentially 90 degrees refraction already, right? So you're supposed to use the formula n equals to 1 over sine c, and from here you're supposed to find that sine c is equals to 1 over n. C will be shift sine 1 over your 1.25. So press that in the calculator, 1.25. Shift sine this answer here. You're supposed to get 53.1 degrees, guys. You're supposed to get 53.1 degrees, which is essentially donkey here. Scientists describe light as being monochromatic, yet again, single wavelength, single frequency. What does this tell you? It has single frequency, won't have more than one wavelength. It won't be in one direction only. It travels at different speed in different directions. This is not possible as well. So logical answer is going to be A here. Don't overcomplicate it. Alright, then looking at the next question here. A source emits visible light. Figure 6.2 shows a ray of red light from the source incident on face XY, so right here, XY here, of a glass prism at point X. The angle of incident I is supposed to be 35 degrees. The refractive index of the glass is 1.5. Calculate the angle of refraction here. Now this is a very simple one. N is equals to sine I over sine R. Right, your sine R will be equals to sine I over N, and your R will be shift sine I, which is 35, divided by your N, which is going to be 1.5 here. So press that into your calculator, sine 35 divided by 1.5, shift sine answer here. You're supposed to get an angle of 22.5 degrees. 22.5 degrees here. Alright, then moving on to the next part. On figure 6.2, draw the refracted rays of X and Y and the ray emerging at XZ of the prism. Label this R. So, and the ray emerging from XZ. So we're basically supposed to have something like this. It's going to bend closer towards the normal. It's supposed to bend closer towards the normal here, right? Then after that, as it emerges from XZ, you're supposed to bend downwards, because yet again you're supposed to bend away from the normal, right? If this is it, then you're supposed to bend away from the normal here. So you know this is essentially what I showed you guys in the notes, guys. You can refer to the notes for this one here. Now after that, it says that A ray of blue light, oh, you're supposed to label this R by the way. A ray of blue light follows the same path as the ray in XY. So the ray of blue light, same path here. On figure 6.2, draw the path of this ray as it emerges from the prism. Now, since blue is a shorter wavelength than red, what's going to happen is it's actually going to bend closer towards the normal, right? Meaning to say, if red was on top, the blue will be at the bottom and it will refract more here. And this is essentially going to be your blue color, guys. All right. Yet again, you can refer to the notes. The speed of light in air is 3 times 10 to the power of 8. The refractive index is 1.33. Calculate the speed of light in the water here. N equals to C over V. V will be equals to C over N, which is 3 times 10 to the power of 8 divided by 1.33. Press that into the calculator. You're supposed to get 2.26 times 10 to the power of 8 meters per second here. 2.26 times 10 to the power of 8 meters per second. Okay. Then the final parts here. Figure 7.1 shows a ray of light in the water that is incident on a submerged transparent plastic. So this is water and this is plastic. You can see that the light ray actually bends closer towards the normal, indicating that the refractive index is higher here. State what happens to the speed of light as it enters the plastic block and explain your answer here. From here, I can say for certain that the speed of light decreases as it enters the plastic block, and my explanation is because the light is bending closer to the normal, indicating a higher refractive index of the plastic. Okay, speed of light. The speed of light decreases as it enters the plastic block. The light is bending closer to normal, indicating a higher refractive index of the plastic. Okay. Then the ray of light traveling in air strikes a glass at 30 degrees to a normal. The light slows down as it enters the glass block. State and explain in terms of wavelength what happens to the light here. Now obviously, as it enters the glass block, the speed of light is going to decrease, right? If the speed of light is going to decrease, what's going to happen is the wavelengths of the wavefronts will be shorter because it is bending at the boundary, and in fact it's bending closer towards the normal, right? So I'm going to first state my statement is that since the speed of light decreases, the wavelength of the wavefronts decreases. This is because it bends at the boundary and the light bends closer to the normal. Yeah. Since the speed of light decreases, the wavelength of the wavefronts decreases. This is because it bends at the boundary and the light bends closer towards the normal. Towards the normal here. Alright. And finally, the speed of light in the glass block is 1.9 times 10 to the power of 8. Calculate the refractive index here. Speed of light in the glass block is this amount. I think straight away you can use the N equals to C over V formula, right? Which is essentially 3 times 10 to the power of 8 divided by 1.9 times 10 to the power of 8. Press that into your calculator here. 3 divided by 1.9. You're going to get 1.58. 1.58 as your refractive index. 1.58 here. Okay? And moving on to the final exercise here. A narrow beam of light is traveling through a transparent liquid. It meets the surface as shown at an angle of incidence 40 here. The refractive index is 1.5. Since this is liquid, this is supposed to be the refracted ray. What is the angle of the refraction as the light enters the air here? Yet again, don't be confused, guys. And whenever you're using the sine I over sine R formula, your I should always be the one that is in the air, and R should always be the one that is in the liquid. So N equals to sine I over sine R. Your N times sine R is equals to sine I, and shift sine N times sine R would have been I lah. In this case here, it will be 1.5 times sine 40, then shift sine this answer here. You're supposed to get an angle of 74.6, which is essentially 75 degrees, correct to two significant figures. Which condition is necessary for light to be totally internally reflected? There are two specific conditions. Number one, the incident angle must be greater than the critical angle, and number two, the incident light should be from more dense to less dense. So looking at this answer here, more dense to less dense is going to be this one, greater than the critical angle, and obviously donkey is going to be the answer here, right? Then moving on. Light is traveling through air. The light strikes a glass block at an angle of 45 degrees. The glass has a refractive index of 1.4. What is the angle of refraction of light as it enters? So light strikes a glass block. Yeah. So this is essentially N equals to sine I over sine R again. This time you're looking for the refraction of the light in the glass, right? So it's sine R will be equals to sine I over N, and R will be just shift sine sine I over sine R, sine I over N, right? So press that in the calculator. Sine 45 divide by 1.4, shift sine this answer, you're supposed to get 30.3, which is essentially 30 degrees lah. Okay. And finally, is it finally? No, not finally. A light passes through a vacuum and enters a liquid. The diagram shows the path it takes. The light travels through the vacuum at 3 times 10 to the power of 8 meters per second. What is the speed of light in the vacuum? Now, if they give you these two incidents, then obviously incident and refraction, you're supposed to use sine I over sine R yet again. Sine 40 divided by sine 25. You're supposed to get a refractive index of 1.52, right? Then after that, using a C over V, which is in the end V equals to C over 1.5. 3 times 10 to the power of 8 divided by 1.52 here. You're supposed to get a speed of 1.97, which is essentially 2 here, guys. 2 times 10 to the power of 8 meters per second here. Okay? And finally, the refractive index of a transparent solid is 1.3. The light is incident on the surface at an angle of 67 degrees. Calculate the refraction of light in the solid. Straightforward, N equals to sine I over sine R. Sine R is equals to sine I over N. R will be shift sine I over N. Press that into your calculator here. Is essentially sine 67 divided by 1.3, then shift sine this answer here. You're supposed to get an angle of 45.1 degrees, guys. 45.1 degrees here. And finally, figure 7.1 shows light approaching a boundary between two materials, speed v. The speed of light after crossing the boundary is 1.3 v. So here it is at v, and then here is 1.3 v. Since the speed is faster here, I know that the refractive index is higher. Determine the angle of incident here. Now, if I'm looking for the angle of incident, since the refractive index is higher here, then this is going to be my R, right? And if this is supposed to be my R, then this is supposed to be my I lah, right? So if I want to find the angle of incidence here, in this case they're asking for this part, which is actually just going to be 40 degrees, right? It's 90 minus 50 is supposed to be 40 degrees here. Then after that, they ask you to calculate the angle of refraction, which you're supposed to employ a few things. Number one, you need to know that this is higher speed than this. So if you use the n equals to c over v formula, it's supposed to be 1.3 v divided by v, which will give you a refractive index of 1.3. With this refractive index of 1.3, you're supposed to use the n equals to sine I over sine r formula, right? Your I will be this one and your R will be 30 instead. So it's going to be like n equals to sine I over sine 30. Yet again, you're supposed to do everything into your calculator here. Right, you'll get 1.3 times sine 30, then shift sine this answer here. You're supposed to get an angle of 40.5. You're supposed to get an angle of 40.5. Oh, sorry, this isn't 30. Lol. This is 40. This is 40 here, and this is 1.3. So it's yet again 1.3 times sine 40. Then you shift sine this answer here. You're supposed to get an angle of 56.7. 56.7 degrees, guys. 56.7 degrees. And that's how you're supposed to answer these questions here.